starting chapter 2, all right? And I want to kind of give you the big picture of where you're going and what we're doing here in chapter 2. And here's the kicker. If you can get the big picture of what we're doing here, it's what is going, this picture is what goes through the whole book, all right? And here's what we do. So, we now have Schrodinger's time-dependent equation. Okay, and you should all be able to do time-dependent. You should all be able to write it down on your own now. And it's H0 psi. And I'm going to be very explicit for the moment with how I write psi. It's a capital psi, and it's a function of x and t, just like a plane traveling wave. All right, and that equals h bar partial of psi with respect to t. And again, put explicitly x and t, so it's a one-dimensional psi for now. All right, H0 is the Hamiltonian, and we're going to spend a lot of time on that as the Hamiltonian. And that represents what, guys?
It represents potential and kinetic energy.
Okay, but more generally, it's the energy as if particle-like, right? It's energy we recognize with particle-like. So the kinetic and the potential energy. And over here, we're kind of thinking about that as being the energy as if it's a wave. Yeah. So if you keep that idea in your head, it goes a long way. So right now we have kinetic energy and potential energy. And we know the operators, it's p squared over 2m plus v. All right. And for the time being, we're going to restrict ourselves. This is an important restriction. All right, we're going to restrict ourselves to time-independent potentials. All right, and then we warned you already many times, this is traditional for the potential energy in the Schrodinger equation V, but it is most definitely not the electrical potential. The electrical potential is not electrical potential energy. Okay, so we'll talk about that.
Time independent what? EP?
We're restricted time-independent potential energy.
Oh, okay.
All right, so in this case, it's just a function of position. And we know the operator from p squared, so this becomes minus h bar squared over 2m in one dimension partial squared with respect to x squared plus bu x. Right? So generally speaking, this is where you start. You start a problem this way. And when you look at the problem, the only thing that changes problem to problem is what?
Potential.
There's the potential energy, really, right? Because the form of kinetic energy is an operator, right? And it pulls it out of the wave function. The potential energy is the thing that's specific problem to problem. Okay. Our goal is always to solve for psi of x comma t, right? We want to solve for that. All right, so this is a PDE, partial differential equation, all right, second order partial differential equation, and we want to solve for psi of x and t. Okay, so what we're going to do is our technique that we're going to use, and we're going to use this over and over and over again, our technique to solve this PDE, partial differential equation, is the standard technique, and it's by separation of variables. Okay? Now, separation of variables is a very general technique. It's not just for this Schrodinger's equation. This is how you can solve any multivariable partial differential equation. All right, but what we're going to find out is that when we do this technique and we solve the Schrodinger's equation by separation of variables, we're going to get very special answers. All right? And in the language that we've already talked about, those special answers are, the answers will form, there'll be an infinite number of answers when we do separation of variables. And those infinite answers will form a complete basis set in function space. And when we have a complete basis set in function space, we can build any answer as a linear combination of those basis vectors, basis functions.
That's what we're going to eventually work.
That's what we're doing. That's the whole technique. Okay? So, the technique is by separation of variables. So here's what we're going to do. The first step in separation of variables is to assume a solution psi of x and t equals g of t, just some function of time, times psi of x. All right? This is very nice Griffiths notation. It's subtle, but once you see it, get used to it, you'll see it all over the place. This is lowercase psi, and what is lowercase psi? It's simply a function of x, all right? It's no longer a function of time, all right? What we will find is this. We will find that g of t equals e to the minus I e n over h bar t. Let me write it this way, e total. So it's e to the minus I, e total times the time over h bar, and the Turing units work out. So therefore, psi, capital psi of x and t, is going to equal e to the minus I, e total over h bar t times psi of x. So this is going to be our solution every time. And, you know, let me emphasize again, it's every time. For whenever you have a potential that's not a function of time, what is the time part of the solution to capital psi? It's always this. It's not going to change. So once we solve it, we'll always solve for these time-dependent parts. All right? So the question is how do we solve for this part then? Right? How do we solve just for the spatially varied part? And the answer is that to solve for psi of x, what we're going to solve is the Schrodinger's time independent. Okay, and Schrodinger's time independent equation is h0 psi equals e total psi. Okay, I've already stopped putting in as a function of x because that's what I'm saying explicitly.
So, you know how in chapter 2, it lays this out, and we're trying to go through chapter 4 this semester?
Yeah, or 5, yeah.
Or 5, but you said definitely 4,
Yeah.
right? And 4 brings all this back with regards to the hydrogen atom?
4 just uses all this, yeah.
Right. What, I mean, so if that's all that there is, all the extra stuff in between is what? Just like detail?
Formalism. Formalism.
All right.
This is just a technique to look at. I went through formalism and where Schrodinger's equation came from. Now what's your job?
To use it.
To solve it. To solve Schrodinger's equation. So that's what the rest of the book is about, solving it. And so this is a good technique to solve it. Okay, so what we're going to do is this. We're going to find that there are an infinite number of psi's. So what we're going to do is we're going to call these psi n, and we're going to rewrite this as h0 psi n equals e total, if you want, n, and psi n. All right? So there's a lot of them. And then what we're going to do is then we're going to say, what is psi n of x and t equal to? So this is the total psi for n. That has to have the time-dependent part and the spatial dependent part. So what is this? We already said the time-dependent part doesn't ever change. Okay, so it's going to be e to the minus I e total, and let's put a subscript n times time over h bar times psi n of x then here's the kicker. So these are called stationary solutions. Okay? The reason why they're stationary solutions is because when you look for expectation values, for example, let's say the expectation value of some operator, what's that going to equal? We've got the formulas. How do you calculate an expectation value? What's that? An integral, right? An integral of what? Make it an integral over x of psi star, then what?